The purpose of the hydraulic filter is to promote long system life by keeping damaging contaminants out of the hydraulic fluid. To better understand how a hydraulic filter works, let's look at the components of a typical spin-on filter. The primary components are a base plate assembly, a bottom end cap, a center tube, the filter media, a top end cap, a compression spring, and the canister. Fluid enters here, is filtered through the media, passes through the center tube, and into the system. Many factors determine the proper hydraulic filter to be installed, including the system's operating pressure, the location where the filter will be used, the type of fluid used, the amount of fluid flow required for system operation, and the fluid cleanliness level, or ISO code, required by the specific application. Hydraulic systems come in many configurations and can be simple or complex in design. Today's heavy-duty hydraulic systems run at higher pressures and faster cycle times than ever before, causing greater system stress and increased sensitivity to contamination. Baldwin provides a wide range of low, medium, and high-pressure hydraulic filters to meet any hydraulic system's configuration. Low-pressure hydraulic filters have working pressure up to 150 psi and burst pressure up to 300 psi. Medium-pressure hydraulic filters have working pressure up to 500 psi and burst pressure up to 1,000 to 1,500 psi. High-pressure hydraulic filters have working pressure up to 3,000 psi and burst pressure up to 6,000 psi. Hydraulic systems are using an increasing number of filters. Increased sophistication and the use of sensitive, closed-tolerance components often require several filters in different locations in the system instead of just one. These filters include suction side filters, pressure side filters, return side filters, and offline filters. Suction side filters, which are located before the hydraulic pump, protect the pump from contaminants in the fluid. Suction side filters may be located in the line between the reservoir and the pump, or may be a wire screen on the end of the pickup line in the reservoir. Some manufacturers do not recommend the use of suction side filters because they can cause cavitation erosion. If using a suction side filter, use a wire screen filter with a higher micron rating. Pressure side filters are located downstream from the hydraulic pump. Pressure side filters clean the fluid as it exits the pump, protecting the more expensive, sensitive components such as valves and actuators from contaminants generated from the pump. Pressure side filters are designed to handle the system pressure. They are also sized for the specific flow rate in the pressure line. Return side filters, which are located between the control valve and the reservoir, are the last components the fluid passes through before returning to the reservoir. Return side filters capture wear debris from the system's working components, as well as contaminants that enter the system through worn cylinder rod seals. Offline filters, or kidney filters, are used on an offline filtration system that is added to the hydraulic system to filter the fluid in the reservoir independently from any other filters in the system. This system includes a separate circulation pump and electric motor that continuously pumps the fluid out of the reservoir, through the filter, and back into the reservoir, providing constant cleanliness levels of the fluid. Also available are intake breathers. Intake breathers are located on the reservoir and prevent contaminants from entering the reservoir while maintaining the reservoir's atmospheric pressure. Breathers prevent moisture and contaminants larger than 3 microns from entering the reservoir. Since most contaminants enter through the reservoir, the use of a breather is a good idea. There are many types of hydraulic fluids used in hydraulic systems, but hydraulic fluids can be broken down into 3 main categories: petroleum-based fluids, fire-resistant fluids, and biodegradable fluids. Petroleum-based fluids are by far the most common fluids used in hydraulic systems today. Petroleum-based fluids have good lubricity and are low in cost and readily available. Most petroleum-based fluids contain additives to help prevent rust, oxidation, foam, and wear. The disadvantages of petroleum-based fluids are low fire resistance, high toxicity, and poor biodegradability. Fire-resistant fluids are used in high fire risk environments, such as steel mills, welding operations, and underground mining, where potential ignition sources such as open flames, sparks, or hot metals exist. Biodegradable fluids are becoming more popular, especially in applications where fluid leakage and spills could have a negative impact on the environment. The most common applications for environmental fluids are agricultural, forestry, mining, and construction machinery, boats and marine equipment, and offshore drilling operations. When selecting a hydraulic fluid, follow the manufacturer's recommendation. The manufacturer has designed the equipment to a certain fluid performance level. Without proper fluid, seals may leak, swell, or prematurely wear out. This can generate heat, causing the fluid to overheat and may allow entry of contaminants into the system. Excessive heat can cause breakdown of the fluid itself. The fluid flow in your system will also be a factor in determining the correct filter use. It is important to have the right size filter to meet your system's requirements. Because fluid can only travel through the filter media so fast, a system with a faster flow rate will need larger filters than a system with a slower flow rate. If the filter is too small, it will not be able to handle the system flow rate and will create excessive pressure drop. This could result in reduced fluid flow on the outlet side of the filter, causing heat to be generated by non-lubricated components. If the filter is too large, it will require more fluid and be more expensive to replace. Particle counting is the most common method for determining a system's fluid cleanliness level. The ISO 4406 code is used by most manufacturers to determine how many particles over the size of 4, 6, and 14 microns are present in a sample of fluid of a known volume, usually 1 milliliter or 100 milliliters. For example, a hydraulic cartridge valve manufacturer may recommend an ISO cleanliness level of 18-16-13 for their product. 18 equals the range of number of particles greater than 4 microns. 16 equals the range of number of particles greater than 6 microns. 13 equals the range of number of particles greater than 14 microns. In this example, to meet the manufacturer's specifications, a 1 milliliter sample of fluid should contain no more than 1,300 to 2,500 particles greater than 4 microns in size, 320 to 640 particles greater than 6 microns in size, and 40 to 80 particles greater than 14 microns in size. A hydraulic filter also has performance requirements to ensure the filter meets or exceeds OEM and customer requirements. These requirements include the amount of restriction or resistance to fluid flow caused by the filter, and the amount of contaminant the filter needs to hold to meet service interval expectations. The filter must be able to work with and not against the system. This means it should create the minimum resistance to flow while maintaining the high efficiency required for good protection. The resistance to flow increases as the filter element becomes contaminated. The filter must be able to provide enough dirt holding capacity to meet service interval expectations. When selecting a filter, it is important to note and understand performance ratings. Overall performance is expressed through micron ratings, beta ratios, efficiency, and capacity. A filter's micron rating is the measurement of the size of contaminant that can be efficiently captured by the filter. Filters typically trap contaminants in the 3 to 30 micron range. Though microscopic in size, these contaminants can cause extreme damage to the system. Remember, something as small as a human hair is 50 microns. Beta ratio describes how efficient a filter is in trapping particles of a certain size. A multi-pass test is used to count the number of particles of a given size before and after fluid passes through a filter. This information is converted into the beta ratio using this formula. In this example, at the 10 micron level, the number of particles upstream is 2,000. This number is divided by the number of particles downstream, which is 1,000. So at the 10 micron level, the beta ratio is 2. Efficiency is calculated by taking the beta ratio minus 1 divided by the beta ratio. This number is multiplied times 100. In this example, the efficiency is 50%. This is a nominal efficiency rating. Efficiency is largely determined by the filter media. Media that is more restrictive will filter out more and smaller particles, thus giving the filter higher efficiency. That same restrictive media, however, may lower the filter's capacity. Capacity is the amount of contaminants the filter media can hold before the pores begin to plug, interrupting proper fluid flow through the filter. Highly restrictive media that increases efficiency allows less fluid flow and, as a result, decreases capacity. So, as efficiency increases, capacity typically decreases. Therefore, a filter with high capacity may have less efficiency. Because of this, filters must be capable of removing the damaging particles while still allowing for proper fluid flow. Understanding the correlation between capacity and efficiency is important when selecting the proper filter. A high efficiency rating with low capacity could result in frequent change intervals. On the other hand, high capacity with low efficiency may lead to early system failure because less of the damaging contaminants are captured. Often, a middle ground between efficiency and capacity is the best place to be. When comparing like products from different filter manufacturers, request comparative test results from standardized tests. OEMs have worked with the filter industry to develop a series of symbols depicting industry-accepted test standards for filter comparison. Hydraulic filters themselves have pictograms showing the minimum performance specifications required to meet service interval expectations. These symbols help ensure that the equipment is serviced with a filter product that will provide adequate protection that matches the OEM for the hydraulic application. These symbols will usually reference a test specification developed and/or approved by an industry-recognized association or professional society such as the ISO, International Standards Organization, the NFPA, National Fluid Power Association, or the SAE, Society of Automotive Engineers. All of these organizations work to develop and improve standards for testing fluid power components such as filters and reporting the results. This is important when evaluating the performance ratings of different filter brands. The four major criteria for filter performance are capacity and efficiency, structural integrity, collapse strength, and resistance to flow. Capacity efficiency is determined by the ISO 16889 multi-pass test. This symbol indicates the contaminant holding capacity in grams of the filter under laboratory test conditions, the efficiency or beta ratio in removing the contaminants, and the flow rate at which the filter was tested. In this example, the filter has a holding capacity of 85 grams of a standardized contaminant. The filter's beta ratio is at least 50% efficient in removing particles, which are 10 microns in size or larger. And the fluid flow rate at which the filter was tested is 1.2 liters per second, or equal to about 20 gallons per minute. Structural integrity, or bubble point, is determined by the ISO 2942 test. This test ensures that the filter media does not leak due to holes or improper assembly. The filter element is submerged in a test fluid and slowly pressurized until bubbles appear. In a successful test, bubbles will pass through the filter media at a pressure relative to the efficiency of the filter media. In this example, the filter has a bubble point greater than 0.75 kilopascal. Collapse strength is determined by the ISO 2941 test. This symbol helps ensure reliable operations by defining the minimum acceptable differential pressure at which a structural failure of the filter element will occur. When a filter begins to plug with dirt or during cold starts, the pressure difference between the inlet, the dirty fluid side, is greater than the outlet, the clean fluid side. This can cause the filter to collapse, which in turn causes unfiltered fluid and damaged filter components to be routed back into the system. In this example, the minimum pressure required to collapse the filter is 1,380 kilopascals. Resistance to flow, or maximum differential pressure, shows the maximum allowable differential pressure of a clean filter element tested at a prescribed flow and fluid viscosity. The resistance to flow through the filter is very important. This resistance or pressure drop has direct bearing on the filter life. Some hydraulic systems contain a bypass valve. If the filter becomes too restrictive, the bypass valve opens, allowing the fluid to be diverted around the filter. The bypass valve is located in the filter or elsewhere within the hydraulic system. As the length of time the filter spends in bypass increases, so does the contamination level in the system, and the greater the risk of a contamination-related failure. In this example, the initial restriction or differential pressure caused by the filter element must be less than 120 kilopascals when using a fluid with a viscosity of 450 centistokes at a flow rate of 1.2 liters per second. A lot goes into choosing the correct hydraulic filter, and Baldwin provides an extensive line of hydraulic filters which meet performance requirements on all types of operating systems. Spin-on hydraulic filters, such as the Baldwin BT287 series, are typically used on the return side on low-pressure hydraulic systems. With the introduction of the Pure Force hydraulic product line, Baldwin provides a new alternative for medium-pressure hydraulic assemblies. The Pure Force product line consists of filters, bases, and self-housed indicators, which allow users to customize filtration systems to meet their individual needs by allowing users to use a combination of bases, indicators, and a selection of quality hydraulic filters. Cartridge-type filters such as the Baldwin H9000 series with synthetic media are used on applications with high pressure requirements. Choosing the right hydraulic filter for your hydraulic system is essential in helping maximize service life and minimize operating costs.